Modern airplanes are truly engineering marvels. They overcome highly turbulent and unpredictable currents in the air and complete their flights by undertaking many complex maneuvers. Have you ever thought of how the pilots are able to achieve this? Or what happens to the airplane when the pilot operates certain controls? In this video, we will explore how an airplane flies and how pilots are able to control an airplane in a logical yet simple way. We thank SimScale for lending their CFD support and making this video more informative. First, let's have a closer look at modern airplanes' wings and tails. One interesting thing you will notice is that they are not made as a single solid piece. The wings and tails of the airplanes have many movable parts. The most fascinating thing about the whole wing and the different parts of it is that they form a very special shape in fluid mechanics. That is the airfoil shape. Just by understanding the physics behind this simple shape will allow you to completely understand airplane physics. Let's learn more about airfoils. An airfoil produces a lift force when moved relative to the air. This lift force makes an airplane fly. How is this lift produced? The airfoil produces a downwash as shown. This causes a pressure difference at the top and bottom of the airfoil, and hence produces lift. This high-quality CFD analysis using SimScale software clearly illustrates this fact. Generally, the higher the angle of attack, the greater will be the downwash and therefore the lift force. A greater airspeed also increases the lift force significantly. Interestingly, in mankind's first successful flight, the Wright Flyer also made use of this same airfoil principle. Even though their airfoils were a simple curved shape, it was sufficient to produce a good downwash. More specifically, their airplane had two such airfoils. One more idea to increase the lift force is by altering the airfoil shape like this. The alteration in shape will definitely increase the downwash and the wing area, hence giving greater lift. In short, there are three techniques to increase the lift of an airfoil. Let's apply this airfoil knowledge to the airplane. If we activate the flaps and slats, it increases the downwash and increases the lift. The ailerons can move up and down, and for that reason, the lift force can decrease and increase respectively. At the tail of the airplane, you can see two attachments, the rudder and the elevators. By adjusting the elevators, you can control the vertical force on the tail. By adjusting the rudder, you can control the horizontal force. Now, let's get into the most interesting part of the video, controlling the aircraft using these simple wing attachments. Let's start with the takeoff part of the flight. To get the airplane to take off from the ground, what you have to do is increase the lift force using various techniques and make sure that this force is more than the gravitational pull. Pilots apply all of the three lift increase techniques together for a successful takeoff. First, the speed of the airplane is increased by increasing the thrust of the engines. When the airplane's speed is high enough, the pilots activate the flaps and slats. Lift is further increased due to this. When the airplane is ready for takeoff, they activate the elevators upwards. The tail force tilts the airplane as shown, and the angle of attack of the airfoil will be increased. The lift is suddenly increased due to this, and the airplane takes off. Usually, an angle of attack of 15 degrees is maintained for the takeoff. In all these discussions, we are talking about the engine's thrust. But how is the engine able to generate thrust? Modern airplanes use special kinds of engines called turbofan engines for this purpose. In this, the fan's reaction and the reaction force of the exhaust give the necessary thrust force. By burning more fuel, the pilot can achieve more thrust. The fuel of an airplane is stored inside the wings. After the takeoff, next comes the climb phase of the aircraft. As long as the engine's thrust is more than the drag, the speed of the airplane will keep on increasing. The greater the speed, the higher will be the lift force. This will cause the airplane to go up. When the airplane reaches level flight, there won't be any acceleration or change in altitude. You can see that with this condition. The thrust should be exactly equal to the drag, and the lift should be exactly equal to the weight of the airplane. Now, let's discuss the most crucial part. How does an airplane change direction? You might think that just by adjusting the rudder, you would be able to do this. The rudder produces a horizontal force, and this force can turn the airplane. However, such a direct change in direction will cause discomfort to passengers, and it is not a practical method. To make a turn as shown, what you need is a centrifugal force. Let's see how pilots achieve this centrifugal force. Pilots just make one aileron go up and the other aileron go down. The difference in the lift force will make the airplane roll. In this roll condition, the lift is not vertical. The horizontal component of the lift can provide the necessary centrifugal force to bank the aircraft. This way, the pilot can make a turn of any radius depending upon the angle of roll and the speed of the airplane. However, this banking technique has some drawbacks. When you keep one aileron up and the other aileron down, the drag forces induced on the wings are not the same. This will cause the airplane to yaw. This phenomenon is known as adverse yaw. The rudder has to be operated simultaneously to prevent the adverse yaw. The way pilots control the different wing attachments and the whole airplane is illustrated in this animation. In practice, a control computer accurately manages all these wing attachments using a fly-by-wire system. To descend the airplane, what pilots do is decrease the engine's thrust and keep the nose of the airplane down. You can see this is exactly the opposite of the climb operation. As the airplane loses speed, it gets ready for landing. At this stage, the flaps and slats are activated again. These devices also increase the drag. To increase the drag further, a wing attachment called a spoiler is also activated. The pilots use one more trick here to reduce the stopping distance, which is reverse thrust. Here, the engine covers open wide, and the air which was supposed to go backwards is forcefully directed forwards. This will obviously generate reverse thrust and will make the stopping of the airplane easier. The CFD simulations we saw in this video were produced by SimScale, a powerful cloud computing-based FEA and CFD software. To perform complex CFD analyses using your normal laptop or PC, just create a free community account at simscale.com and explore. Please check the description. Thank you.